Welcome to the Explainer. Today, we are cracking open the Principal Examiner reports for Cambridge AS and A-Level Physics 9702, and we're translating all that dense academic feedback into a highly actionable, high-scoring exam strategy for one-dimensional and two-dimensional momentum. And honestly, this applies right across the board, whether you're tackling syllabus code 0625, 0652, 0654, 0972, or 5054. The foundational rules are the same. We are calling our overarching strategy today the jazz musician. Why? Well, think about it. A master jazz musician doesn't just play random notes. They can only improvise brilliantly because they completely, intimately understand the underlying musical structure. They know the rules inside and out before they creatively break them. In Cambridge Physics, you need that exact same mastery. You need to improvise your answers within the strict structure of the exam's marking scheme. To set the stage, imagine a dynamic split screen right now. The clock is ticking down, the tension is high, and we are looking at a real Cambridge Physics past paper question. On one side, we have a student we'll call Alex. Now, Alex panics and overloads his answer with raw physics facts. He just brain dumps every single equation he's ever memorized about momentum, but he provides absolutely zero analysis of the specific question in front of him. On the other side, we have Sam. Sam rushes, Sam completely ignores the command word requirements, words like deduce or show that, and ends up leaving massive, easy marks on the table. In this explainer, we are going to show you exactly how to avoid those devastating red pen marks that Alex and Sam are getting right now.
Look closely at this number, 15%. That is massive. This single topic, linear momentum and its conservation, accounts for approximately 15% of your total marks in Paper 2. Think about what that actually means. Nearly 1/6 of your entire grade for this paper rests entirely on your ability to understand objects colliding, sticking together, or bouncing apart in both 1 and 2 dimensions. It is an absolute necessity to master. This isn't just some fringe topic you can cram the night before. It's a core, weight-bearing pillar of the entire Cambridge Physics syllabus. Examiners actively, intentionally, use this specific topic to separate the top-tier candidates from the rest of the pack. Why? Because it perfectly tests your ability to combine raw mathematical execution with deep, conceptual, physical intuition. When a radioactive nucleus decays and the fragments shoot off at different angles, or when two ice skaters push apart, you're not just doing math. You are proving you understand how the universe balances its physical ledger.
So, why is this so hard? Examiners consistently note in their principal reports that applying these theoretical concepts to new, totally unfamiliar contexts is a major hurdle for students. You see, it's one thing to memorize that momentum equals mass times velocity, but the absolute second the exam presents a weird, unfamiliar context, maybe a satellite docking sequence in deep space or subatomic particles colliding in a particle accelerator, panic sets in. Alex, our fact overloader, just starts desperately throwing vector equations at the page, hoping anything sticks. Sam, on the other hand, calculates a quick scalar number, completely forgetting that momentum is a vector quantity and totally ignores the direction. Neither approach works. So today, we are going to build a completely bulletproof mental scaffold. We're going to turn those unfamiliar, scary contexts into recognizable, easily solvable puzzles. Here is our roadmap for mastering this. First, we'll establish the theoretical foundations. You have to know the rules to play the jazz, right? Second, we'll build our procedural framework. Third, we'll dive into critical analysis. And finally, we will break down the ultimate safety net, the method mark strategy. Okay, let's dive straight into Section 1 and build those theoretical foundations. The theoretical architecture of a perfect answer relies absolutely on precise definitions. You have to explicitly state that linear momentum is the product of an object's mass and its velocity, and crucially, you must treat it as a vector quantity. Direction matters. Furthermore, you must establish causal relationships. You need to show you understand that a net external force causes a change in momentum over time. That's literally Newton's second law in its purest form. But here is the real secret sauce, the thing that bumps you up a whole grade boundary: integration. Candidates who reference cross-topic connections achieve significantly higher marks. For example, can you connect the kinetic energy lost in a totally inelastic collision directly to the work done deforming the objects? That's what examiners want to see. Now, to structure all this, we use the PEEL framework: point, evidence, explanation, link. You make your point about momentum conservation. You pull the evidence straight from the data table. You explain the physics principle governing it, and you link it right back to the question's specific context. Let's do a quick interactive check right now in your head. If a question asks you to deduce if a collision is elastic, and you just write, kinetic energy is lost, is that a PEEL answer? No, that's just a point. A PEEL answer says, the collision is inelastic,
Point? Because the initial kinetic energy was 50 joules, but the final is 30 joules. Evidence. Meaning kinetic energy is not conserved despite momentum being conserved. Explanation. Which proves this specific two-car collision resulted in energy dissipated as heat and sound. Link. See the difference? Before we continue, subscribe to our YouTube channel AC Exams at ACExams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
We are literally reverse engineering the Cambridge assessment objectives here. These targets hit 3 distinct cognitive domains. The first is knowledge and understanding, recalling foundational theory, like stating the principle of conservation of momentum. The second is application. This is where the transformation from a struggling student to a top-tier candidate happens. Application means taking that theory and adapting it to the unfamiliar context we talked about. And the third is analysis. This means prioritizing depth over superficial breadth. The examiner does not want 10 random disconnected facts about momentum. They want you to execute the physics success blueprint, read the command word, select the exact right concept, and apply it deeply. Think back to Alex and Sam. We are actively changing their red pen marks into green check marks. We take Alex's brain dump, cross it out, and replace it with 3 highly targeted sentences. We take Sam's rushed math, add the vector directions, and instantly secure the analysis marks.
Moving right along to Section 2, let's look at the actual procedural framework for the exam. But real quick, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's get into our interactive workshop. When tackling complex physics problems, you absolutely need a step-by-step procedural framework to keep you grounded. Step 1, deconstruct the question. Decode those command words. Calculate means show the math. Explain means use words to justify the physics. Step 2, extract relevant data. Pull those masses and velocities out of the noise. Step 3, select your analytical framework. Are we in 1D or do we need to resolve vectors using sine and cosine for 2D? Step 4, execute with clear notation. Use U for initial and V for final velocity. Step 5, present with correct terminology. Never just say it went backwards. Say the velocity vector reversed direction, yielding a negative value. Let's do challenge 1, the data scan. Imagine a complex data table showing a 2D collision between 2 gliders on an air track. You have 60 seconds on the clock. What's the core trend you need to extract? You need to scan the x components and the y components separately. If the initial y momentum is 0, then the final y momentum of the scattered gliders must cancel out to 0. Boom, that's the core trend. You scan, you extract, you set up your framework.
To lock this framework in, use this memory hack during the sheer stress of the exam, the visual story method. Mentally picture the collision before you ever touch your calculator. Visualize 2 billiard balls. See the angle of impact. Now, let's try challenge 2, find the flaw. I'll read a sample paragraph, you find the mistake. The 2-kilogram ball moving at 3 meters per second hits the stationary 1-kilogram ball. After the collision, the total momentum is 6 newton-seconds, and because they bounce off each other, the total kinetic energy must also be conserved. Did you spot the flaw? Just because objects bounce off each other does not mean kinetic energy is perfectly conserved. It might be an inelastic collision, where they don't stick together, but energy is still lost to deformation. That single flawed assumption will cost you major marks. Let's move into Section 3, critical analysis and evaluation. This is where we secure the highest possible grades. When an exam demands comparative analysis, like comparing an elastic collision to a totally inelastic one, you must explicitly identify both similarities and differences. It is not enough to just say one loses kinetic energy. You must explicitly state that in both scenarios, total linear momentum is conserved. You need to use comparative connectives like whereas, conversely, or however, and you must support this with evidence. Time for challenge 3, speed writing. You have 30 seconds. Mentally draft a perfect Peel paragraph comparing the momentum of a photon to a massive particle. Go. When an exam demands comparative analysis, like comparing an elastic collision to a totally inelastic one, you must explicitly identify both similarities and differences. It is not enough to just say one loses kinetic energy. You must explicitly state that in both scenarios, total linear momentum is conserved. You need to use comparative connectives like whereas, conversely, or however, and you must support this with evidence. Time for challenge 3, speed writing. You have 30 seconds. Mentally draft a perfect Peel paragraph comparing the momentum of a photon to a massive particle. Go.
A perfect problem-solving approach moves through 3 levels. Descriptive, you identify the given info and break it down. Analytical, you solve systematically and check for reasonableness. Seriously, if you calculate an ice skater moving at half the speed of light, stop and check your math. Evaluative, you compare approaches and make justified recommendations. If you follow this deconstruct, solve, evaluate method, your problem-solving becomes absolutely bulletproof. You're no longer just guessing. You are systematically dismantling the question just like the examiner designed it to be dismantled. Finally, we reach section 4. These are the direct examiner warnings and the crucial method mark strategy. This right here is the final system. We have 3 rules that essentially guarantee top marks. Rule 1, command word decoding. Rule 2, Peel framework application. Rule 3, the time management matrix, meaning you allocate exactly 1 minute per mark. And if you get stuck, you move on and come back. Examiners warn us every year about the same mistakes: vague, contextless answers, poor formatting where your numbers are just floating all over the page, ignoring the specific context. You absolutely must tailor your specific details perfectly to the given context. Define your system, explicitly state which direction is positive, and clean up your algebraic steps. This quote is your lifeline. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. This is the core of the method mark strategy. In complex 2D vector resolutions, dropping a negative sign is so easy to do. If you only write the final answer, you get a 0. But if you show your procedure, you catch the safety net. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. So, how will you structure your analytical framework for your next calculation? Will you rush like Sam, or will you play like the jazz musician, mastering the structure to execute perfectly? Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGC and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.